Today I will teach a little bit and then we'll have a problem solving session. So it's a short lecture. And on Thursday it will be the quiz first from 5 to 5:20 and then Professor Pal will teach the rest of it. Okay, I hope that clarifies things. So today, like I said before, I will do the energy time uncertainty principle in a little bit more detail, because although it looks the same as the position momentum uncertainty principle, there are some differences in the details and also in the implications. And this is something that is normally not emphasized, but I wanted to just show you this. So if you remember, I told you that the mathematics of the uncertainty principle, which gives rise to the mathematical inequality that delta x, delta p is always greater than equal to h cross by 2, that comes from the mathematics of errors, and the relevant general inequality is this, where if Q and R are two quantities, say Q is position and R is momentum, then the variance, so sigma square is variance, if I talk in statistical terms, then sigma Q square and sigma R square is always greater than equal to 1 by 2i, I being the imaginary number, expectation value of the commutator of Q and R whole square. So this is the general uncertainty principle. Uncertainty principle for conjugate variables Q and R. Okay, this is also related to the Fourier transforms, but we're not going to go into that much detail also. So one pair of conjugate variables is momentum and position, and we have seen that the errors in momentum and the errors in position, they're always greater than equal to h cross by 2, h cross being the reduced Planck's constant. The other pair of conjugate variables commonly used in quantum mechanics is energy and time. Okay, so delta E, so error in energy and error in time. You must have studied this also before in your +2, that the product of the errors there are also more than equal to h cross by 2. But you see, the main problem here, which is immediately apparent, is if I want to derive delta E delta t greater or equal to h cross by 2 from this relation, the general mathematical relation, then we need an operator for energy, which is the Hamiltonian, no problem. But we also need an operator for time. But time does not have any operator in quantum mechanics. So how did we come to this uncertainty principle?
Ma'am,
Yeah.
that general uncertainty principle, is that a postulate, or I mean,
No,
how?
it's derived. It's from mathematics, even classical mathematics, I can say.
Okay.
And okay, ma'am, I also wanted to ask that, ma'am, how does T behaves when we get a stationary value for the energy?
When you get the stationary value for the energy, then T becomes the delta T becomes infinity. So that is what you had studied, right? That if you have a stationary state, then and T is then the lifetime of the state. So if you're in a stationary state, the lifetime is infinity. So delta T is infinity. So that is sort of the interpretation. We'll come to that. Just wait a minute. We'll come to it. Okay, so the main problem here in deriving delta E delta T greater or equal to h cross by 2 is that T does not have an operator. Now, so T No operator in quantum mechanics. So how does time feature in quantum mechanics? So you have the time evolution of a quantum state. So even a stationary state evolves in time. So let's see. So I'm just talking about time in quantum mechanics now in general. So time, I wanted to write evolution of a quantum state. I guess you have come across this when
And
Professor.
how does this system evolves even if it is stationary? I mean, wouldn't stationary imply that it should not be changing and because the probability is one for that eigenvalue?
Okay, so let me clarify this. So a stationary state is not a static state. It's different. A stationary state does evolve in time. So the electrons are moving in time, if you want to think of it that way. So, but the observable values, like if you see the average position or the average momentum, so that's why you always talk about expectation values. These don't change. If you have a non-stationary state, then even the average position and the average momentum, these will turn out to be a function of time. For a stationary state, these are constant values, not a function of time. But they are not static. What the only value that doesn't change for a stationary state is the energy of the state. Everything else is dynamic. Okay. So and this factor here, which is called the phase of the state, this determines how the wave function changes, and then you use this wave function to determine the
Ma'am,
properties
is
of
there
the
a
state.
negative sign e to the power minus or
Uh, well, okay, yeah, that's fine. How you want to do it. So this does not. So what this does is it moves the wave function in a function space that changes everything except the energy. Okay, and it is such, and because this is an imaginary factor, whenever you take expectation values, this factor cancels out. Okay, because you have a star. So you have complex conjugate from the bra function and the and just e to the power minus I e t by h cross from the Keck function. So they will always cancel out. But the wave function still evolves in time. Okay. And if I talk about a non-stationary state, so this is a stationary state I'm talking about. Or let's say, okay, and if you have a non-stationary state, which is also, you can also call it a super imposition of eigenstates, then this time evolution factor is e to the power minus I delta E t by h cross, where delta E is the energy difference. Let's say I'll simplify this to two eigenstates. An energy difference between the two eigenstates. So this is just about the state.
Ma'am, someone raised hand.
I didn't follow, sorry.
Ma'am, someone here was raising hands, so I thought I should tell you because it should
Oh,
not be
yeah,
visible.
I'm not looking at it. Someone was raising hands, so who? Please ask your question, whoever it was. I cannot really follow who raises hands because I'm in the share screen mode. So just speak up. No? Okay, okay, then I'll just continue. But anyone who has a question, just speak up, because if I'm sharing the screen, I really cannot see who is raising a hand or who's messaging. Okay. So, okay. So, like we got the question, even in a stationary state, things are dynamic. And what is changing with time? So, it's the wave function that is basically changing with time. And it is this evolution or this change in the quantities or properties of the system, in terms of which we have to talk about time evolution. Okay. So, if for a general state, okay, let's say I'm not talking about a stationary state. So, say I am following some particular property of the system for a general quantum state, okay, not a stationary state. Then I have an observable Q, which is changing with time. So there are two things that can change with time. One is that the operator for this observable itself can be changing with time. So it is a time dependent property itself. Or you can have the expectation value of this operator changing with time. Or it can be both. So what is the difference between the two? One is that the operator itself is a function of time in the first case. And in the second case, the operator is independent of time, but because the wave function is a function of time, the expectation value becomes a function of time. So again, remember, this is not a stationary state. If it was a stationary state, then the expectation value would be automatically independent of time.
Ma'am, but how does it make sense to say that operator is changing with time? I mean, operator is an instruction for the wave function, right? So, I mean, should it be operator acted upon the wave function is changing with time? I mean, that way.
That is the second one. So the first one is where the operator is it's a time dependent operator.
Uh, Ma'am, but operator itself, I mean, it's just an instruction, right? I mean, how what does it mean that it's changing with time? I mean, can you give an example?
A time dependent operator can be, for example, so if you have a time dependent external field, for example, in the Hamiltonian, then
Okay,
any
so V of
property
x comma
related,
t, something like that.
yeah. So the operator, so that V of it can be a function of both position and time, for example. So it may just be a multiplicative operator. Doesn't necessarily have to be anything
Okay.
special. Yeah. So it can be. Okay. Uh, Fine. So these are the two things that can be dependent on time, or it can be both, or it can be neither. Then let's see what are the contributions to have an expectation value that is dependent on time. Then I will do ddt of psi q psi. And so this is like a scalar product. So you have, so this is an integral. So the derivative will operate on every term in the integral. So I can have del psi del t q psi. This is one term. Then I can have psi del q del t psi. And you can have psi q psi. Sorry. Let's Now, we also know the time-dependent Schrodinger equation, which is IH cross del psi del t is equal to H psi. Now, if I use this relation, I can again write dq dt as so H is Hermitian, so I have not written an H dagger. If it wasn't, then I would have had to write a dagger when I place it in the bra side. And then I simplify this a little bit more. So okay, so when I take out this 1 by IH cross from the bra, I have to put a minus sign because I'm doing the complex conjugate over here. This is minus, and then I have H psi, Q psi. And I have 1 by IH cross psi QH psi. I can write it like this. This I can also write as psi HQ psi. Okay. And I have this as well. So I'm using now a shorthand notation for expectation value of del Q del T. HQ minus QH psi. Okay. And HQ minus QH. Now you have learned.
Ma'am, can you please show a little bit upward? Just for a second.
More?
Okay, ma'am. No, ma'am. It's fine. Okay. I got that.
Okay. And now you know
Ma'am,
that this, yeah?
ma'am,
Yeah?
the equation that you have just written, can you write it in the normal integration form?
Yes, ma'am. It is getting a little bit confusing.
Okay, so let me just simplify this one more step, then I'll write it in integration form. So this HQ minus QH operator, you have now learned that these are called commutators, I guess. So it will be psi. Oof, this is very irritating. Okay. Psi HQ commutator psi plus expectation value del Q del T. Okay, see what you want me to write this in integration form? That is okay. If you want it. And then, since this is a general operator, I can't give you a expression for Q. So psi. Yes. So this is the first term. So let's say, so I'm writing X if you want it in one dimension. If you want multiple, then I can write dr if you like. And then plus
No, actually, in the previous steps where you took out the, I mean, where you manipulated that.
Uh,
From here, yeah, from the top of the page.
so you want. Okay, so you're a little bit confused about moving these things around.
Yes, 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 yes.
Yes, ma'am.
Okay, okay, okay. So let me see. So So maybe if you want me to, so dq dt is like this. And then I used the fact that del psi del t is equal to 1 by IH cross H psi. So I put, so this one, I converted to this one using this relation. Okay. Then, so since H is Hermitian, so normally, let's see. So if you have psi a psi, this basically means psi star a psi. Okay, integrations, whatever. Okay. Now, if I want to act a on psi star, then I have to move a over here. Okay. But then I have to write a psi. Okay, let me do it. So from here, this is this. And if I have a psi psi, that is equal to integration a star psi star psi.
Do you mean A dagger or A star?
Okay, well, if I write it in integral notation, then a dagger doesn't make sense, but typically it is, yes, a dagger. So if I wrote it in a matrix form, then the dagger would make sense. If it's in an integral, then a dagger is nothing, is not different from just a star. So it depends on what notation I'm using. So even for size, if you have the psi as a matrix and then you take a dagger, then it makes sense. If psi is just a function, then a dagger is basically a star. So it depends on the details of the notation. Typically, you can use this notation interchangeably. It's not wrong to write a dagger psi star psi. And psi a psi, that is equal to integration psi star a psi. Okay, so this is a part of the bracket notation, and this fits in with all the manipulations that you do. So if you did everything in integral form, that would also work.
Okay, ma'am. One last thing I wanted to ask, that here in the ma'am, in the next page, first line,
Yes.
ma'am, here H and Q are operators. So, ma'am, is it all right to take them common like this, like numbers? Like here we have taken them and putting minus and putting commutator here. So, is it okay to take common from both the terms because they are operators, and like
Yes, yes.
differentiation is also operator, so we cannot do with that, I think.
Yeah, as long as you're not changing the order of the operators. So you cannot write HQ as QH, but you can take common. This is an overall common thing. It's like if you have a operator even in the integral, you can take that common. This is fine. But okay, so let me just clarify. So here we have psi, the same psi on both sides. even if you had different size, but let's say they were, so I'll erase it afterwards. Okay, don't copy this. If this was like psi I, psi j, and this was also psi I, psi j, then also it is fine. But if you have psi I, psi j, and then psi j, psi I, for example, then you cannot take common. So everything else has to be exactly the same before you take common. Yeah. So what we arrive at is basically a little relation between the time dependence of the operator and the time dependence of the expectation value. So this is the final relation that we get. And we can make some important conclusions from this. So let's see. So let's take some cases. Case 1. If Q is not a function of time, then this last term, so this one is 0. Okay. And then dq dt depends on the commutator of h and q. And if the Hamiltonian commutes with this operator, then even the expectation value of the observable q becomes independent of time. I guess you can see that. If q is not a function of time, the last term is 0, then the rate of change of the expectation value depends on the commutator of the Hamiltonian and q. In addition, if q commutes with h, this means that the commutator of h and q is 0, then the expectation value of q is also independent of time. So case 1, and then I can say this is case 1b, or 1, what should I say, case 1 prime. Now, when we're talking about, so now I will now specialize to a situation where my operator itself is not dependent on time. So now case, okay, some following. So this is in brackets. Now I'm continuing case 1, okay. So in case 1, we have the operator independent of time, but I am not saying anything about the commutativity of h and q. I'm letting that be. Then we can go back to the uncertainty relation, the general mathematical relation. So let's say I'm taking the uncertainty between h and q. Then this is greater than equal to 1 by 2i commutator hq whole square, expectation value of this. Then this is equal to 1 by 2i, and using this relation, I can write that the expectation value of H and Q is basically minus I H cross. Okay, this is becoming a little bit untidy. I'll just write it a little bit cleaner. So I have 1 by 2I, expectation value of commutator of H and Q, whole square. So this is 1 by 2I minus IH cross dq dt. Okay, this is also whole square. So this is whole square. Okay, this has become a little bit clumsy, but I guess you can follow. It's not that bad.
Could you move to the previous page for 1 second?
Ma'am,
Yeah.
phi and phi conjugate were also there. Where are they? Because now there is only commutator, no? There were in the original equation there were phi and phi conjugate were also being there in the integration.
Yeah, there's the expectation value. So that is there still. I'm still writing expectation value. So psi star psi is there. It's still there. And here also in the relation.
Ma'am, this case is not clear. I mean, you said that this is the case when H commutes with Q, right? Or
No. I just so I'm just dealing with a situation where Q is not a function of time. But I have not said anything about the commutator of H and Q. This was just a side note that if Q commutes with H, then automatically the expectation value of Q is also independent of time. So that's like
okay. So the case is that del Q by del T is del Q operator by del T is 0, and other things may or may not be.
Yeah, other things I'm not saying anything about. And I'm trying to find out the uncertainty in energy and the uncertainty in Q, the relation between them.
Ma'am,
Yeah.
I mean, how does this formalism resolves the issue of uncertainty in time?
Okay, so I am doing now a general derivation for any operator, and we find that it is related to the commutativity of it. So we will see how it comes to time. We will see.
Okay, ma'am. Okay.
So far what we have got is uncertainty in energy, that is sigma h squared, and how that relates to an uncertainty in any other property Q. I have not said what Q is so far, but what I have said is that the time evolution of a state is related to how some observable quantity changes with time for that state. Time itself you cannot quantify for a state because, like I said, there is no operator for time. So the effect of time is always on some property. So here we are taking that general property to be Q. Okay. So anyhow, whenever you talk about time evolution, even in a classical case, you're always talking about something that is changing with time. Time itself you cannot measure for any system, even classical. So that is the problem with talking about an uncertainty in time. Time of what? So here we are saying that this time is a time or is related to the rate at which some property is changing. So we'll make it more precise in a little while. Okay. So here what we have done is we have written this general uncertainty relation for in terms of the commutator of the Hamiltonian with the operator for some observable Q, a general observable Q. Okay, and if we simplify this a little bit more, we will get h cross square by 2 2 squares, so that's whole square dq dt whole square. And if I take a square root now, then I can say that sigma h into sigma q is greater than equal to h cross by 2 and magnitude of dq dt. So this is my final general uncertainty relationship for some observable which is not the operator for which is not directly dependent on time. Okay. So sigma h is basically related to the uncertainty in energy. That is fine. But what about delta t? So we define delta t as follows, that it is the uncertainty in Q. My handwriting is terrible when I write it. Divided by the rate of change of Q. Does this make sense? So at least dimensionally, this is fine, right? So,
Ma'am,
yeah.
so actually, as we have no operator, we are defining time from another operator. So
Yeah, any general operator which is an observable for the state, and we are saying that our uncertainty in measuring that property is related to how fast that property is changing with time. And we are calling that the uncertainty in time for that state itself. So you have to think a little bit here. So it's so how do I know that a particle is in a certain state and that the state is not changing? To know that, I have to measure some properties of the state. So let's say I choose one particular property Q, okay, or a whole set of properties, various Qs. I'm measuring all of them, and if these properties are changing very rapidly with time, then my uncertainty in those quantities will also increase. Okay? Which means that the state itself is also evolving very rapidly with time. So it's a little bit of a indirect logic, and that
Ma'am, you
quantifies
say,
uncertainty in time.
ma'am,
Yeah.
ma'am, you are saying that uncertainty in time corresponds to how fast the system is changing. But you said that when it is infinite, then the system is not changing. So how does it make sense in case of the stationary value of energy?
Okay, this is not a stationary state. If it was a stationary state, then delta t is infinity. So this delta t uncertainty relates only to non-stationary states. For a stationary state, delta E is 0. Energy doesn't change. And delta T is infinity, which means it will stay forever in that state. So now we are only talking about non-stationary states where it's changing. And to figure out how it is changing, we have to measure some properties. So delta T, if you remember before, you called it the lifetime of a state, right? So if you're talking about the lifetime, if it's a stationary state, the lifetime is infinity. If it is a non-stationary state, it has a finite lifetime. But how do you measure this lifetime? You have to measure some property for various times, and then you can figure out if it's changing or not, or how fast it is changing. Okay.
Ma'am,
Yeah.
ma'am, in delta t is equal to uncertainty in q divided by the rate of change of q. Is it the rate of change of q, or is it the rate of change of the expectation value of q? Because we consider q to be a time independent operator, right?
It is expectation value of Q. So if I write the next line, then it will become clear. So it's this. This is it. And we are saying delta T is equal to this. So delta T is delta T is basically the time for which the state is residing, or the system is residing in a particular state. It is the lifetime of a state. Lifetime of a state. Okay. And then from here, okay, let me just continue one more and then we'll talk about again the implications. So then delta sigma q can be written as delta t into dq dt. Fine. And therefore, sigma h, sigma q is equal to delta. I don't know what happens. It is equal to delta E, delta T, dq dt. Okay. And my inequality tells me that which means delta E, delta T, dq dt is greater equal to h cross by 2 dq dt. So this was my inequality, remember? H cross by 2 multiplied by dq dt. And then I can cancel these two. And I end up with delta E, delta T greater equal to h cross by 2, which is my final inequality. Okay. So delta T is basically related to the observable which is being considered. It is not an intrinsic time for a state. There is nothing called intrinsic time for a state. And Q is basically any observable. So you can take a whole set of Q. So any set of properties you want to characterize your quantum state with.
So, ma'am, then for different Q, we can have different value of uncertainty in time.
Not really, because you see this inequality, the Q is basically getting cancelled from it. So that is a important observation, that it doesn't matter what Q it is.
But ma'am, in the very definition, there is a role of Q. I mean, so then, I mean, in very definition delta T, there is Q. So how can we avoid the role of Q in?
We are avoiding the role of Q because ultimately we're ending up with a relation with the uncertainty in energy. So if we want to, so what we're saying is that more or less that whatever property we use to track our state, ultimately it is the energy evolution of the state which decides the lifetime of the state. So we're sort of reinforcing the fact that energy is a more fundamental property than other properties. That is sort of what we are finally arriving at. Because Q is getting cancelled from the inequality. The inequality is independent of which property you are measuring. If you actually want to talk about the error in Q related to the error in time, like this relation, that sigma Q is equal to delta T into rate of change of Q, then yes, then it matters which Q you are talking about. But you see, sigma Q is getting converted into delta T. So let me tell you the full implication. So Q is any observable. And so when we call delta T the lifetime of a state, we are basically considering any of the observables of the state which are evolving in time. Now if a system changes rapidly, then dq dt is large for all Q's. Okay. Which implies that delta T is small and that delta E is large. A system can only evolve rapidly if it is a superposition of many different energies. So this is sort of what does delta E large mean? Delta E large means that this non-stationary state has a very wide range of energy. So it means that it is a superposition of a large number of states of many different energies. And the wider the gaps between the energies of the components, the more rapidly the state evolves. So that is the conclusion that we arrive at. That the time evolution of a non-stationary state depends upon the components of that state. And if these components have a wide range of energies, then this non-stationary state changes more rapidly. Okay? Now, if a system is stable, then dq dt or ddt of expectation value of Q, it's small. Then delta T is large, which implies delta E is small. Okay, and if delta T is small, then all dq dt is small. So I think that is the crucial point. That it's all or any, however you want to put it. So any property will have a slow evolution with time. And if I specialize to stationary states, then delta E is 0 and delta T is infinity, like I mentioned before. So I'll put them down. So unfortunately, this took a very long time, but it's an interesting point. So I hope you appreciate it.
Ma'am, so definition of delta T is that, we have our observable Q, which is, the expectation value of observable Q, which is changing with time. So, that rate of change we know, and we know the uncertainty in the observable also. So we are roughly saying that, the lifetime delta T should be, rate of change of that observable times the lifetime. That should be the spread of the Q, something like that, right?
Yes. Sigma Q is equal to delta T into this. Yeah.
Okay, so the spread is the rate of change times the time for which it changes. So that's okay.
Yeah. So we are deriving the uncertainty relation using a particular property Q, but eventually we see that the property itself, or what property we are considering, is not important. Well, the uncertainty in or the rate of evolution of the state is related to the spread in the energy of the state eventually. But in order to track it, of course, we have to use one or more properties. because you see, you cannot measure delta T. You will always have to measure sigma Q if you actually think of doing the experiment. Then you will always get sigma Q as one observable quantity and dq dt as another observable quantity. There is, you cannot measure a delta T. However, this delta T is like whatever Q you use, you should end up with the same delta T, because it is related only to the spread in energy of the non-stationary state, which is one particular thing for the state. Doesn't depend on which property you are measuring.
No, ma'am, I think delta T will depend on the choice of Q. Only the bounds will remain fixed. I mean, delta E, delta T greater than equal to H cross by 2. I mean, only this will remain fixed, I think. But delta T should depend on the Q we are considering. I mean, the literal value of delta T that we compute.
The literal value that you compute, not so sure. I mean, if you worked it out the other way, like if you knew what delta E was, you would be able to figure out what delta T is, right?
No, ma'am, only the bound, right? We'll only
Yeah,
get an
the bound. Yes,
inequality.
yes. I mean, yeah, this is not an equality, the bound. But whenever you use an inequality, you always use the equality, right? You don't really use the inequality.
Yes, ma'am. So that's why I
Yeah.
was saying that delta T would depend on Q, but the only the, I mean, the limits are fixed by this relation.
Yeah, well, if you want to be very precise, yes, only the limits are fixed by this. So delta T is free to be larger. That is true. But I'm not so sure about if it will be very different for different properties. Maybe I'll think about it a little bit more. I'm not so sure. You may be right, but I'm not so sure. The bound is definitely fixed. There is no doubt about that. Whether the actual value of delta T should differ, not so sure. Okay, let me think about this and I will get back to you. Okay, so let me just summarize the observations because you might not remember. So let's see, delta T is related to the observable. Is Professor Pal here? Can someone check? Okay. If dq dt is large, it implies that delta t is small, which implies delta e is large. A system can only rapidly this completes this, and we're already past 10 o'clock. I'll stop here and I'll wait till Professor Pal joins. Okay.
Also, ma'am, that generalized uncertainty principle which you were saying, I mean, it was not derived actually as of yet. So,
No, I didn't derive it. I mean, I myself have never derived it on my own.
okay.
It's related to quite a lot of mathematics. If you're interested, you can look it up. But for the purpose of the course, it is not necessary.
Ma'am, could you please do that slide once again?
You want me to share the screen again?
Yeah.
Yeah. Like below. So which page do you want?
Ma'am, little lower. Last part.
Last part.
Okay, ma'am, got it. Thank you so much.
Okay, so your mid-sem timetable is also out. So let's see. Okay. So it's Saturday, 18th September, 3 p.m. to 4:30 p.m. Mid-sem. Oh. So then we're a little bit short of time.
Ma'am, can we little bit go up?
Sorry. Okay. More?
Ma'am, wait here. Ma'am, there one if del Q del T is large, del T is small. Yes. Okay. Small del is large. Okay, ma'am, got that. Thank you.
Okay. So should I? Okay, let me just call Professor Khan.
Ma'am,
Yeah.
ma'am, I was thinking about one thing that you said that we cannot measure the intrinsic time of a system, but then how can we define the dq by dt? Because we can define change in q, but how can we say that this will be the change in q with change in t? Because there is no intrinsic t in the system.
Okay, I think how should we measure dq/dt? So you can take a reference time, of course, but you cannot measure time for a state. I mean, you always have a reference time, so you can find out dt. But since you cannot measure t, you cannot find out delta t. So you see what would you call delta t? If you're measuring time, you say this is time right now is time equal to 0. And after 2 seconds, your time is 2 seconds. I mean, it's not related to the state. So what you need to know is if your state is changing or how fast it is changing. And to know how fast a state is changing, you need to find out some property of the state. So that is the difference between dq dt and delta t. So if you so let's say, so I'll tell you what can be confusing. So in spectroscopy, you see there are experimental techniques which tell you that they're measuring the lifetime of a state. But then they know exactly the two states between which the system is transitioning. So that delta t is basically between two fixed states. But to identify when the system is in state A and when the system is in state B, they're still measuring some property of the state. Okay. Do you get the difference? I mean, you need to identify the change of the state. So just
And this last part, could you explain again? Like after we got the delta E delta T greater than equal to h cross by 2. Could you explain that once more?
This part, okay. So the fundamental problem in this whole energy time uncertainty principle is that you cannot measure time for a state. Okay, you can have a reference time, and then you can. How do you know that a state has evolved in time? You have to measure a property of the state. That is the fundamental thing that you have to understand. And when you're measuring a property, it can be any property, which I'm calling Q. Okay. And how fast that property is changing tells me how fast the state itself is changing. And we are mathematically writing this as the uncertainty in measuring this property as the as dq dt, and we're relating the uncertainty in measuring the quantity, which is sigma q, to the time evolution of the state delta t multiplied by the rate of change of that property. So we are relating the evolution of the state, which is the quantity delta t, to the rate of change of the observation that we're doing for the property q. And since there is an uncertainty involved in measuring this quantity, we have sigma q, which is the uncertainty in measuring q. And that is why we're not saying this is t, but this is delta t, which is the uncertainty in the or the lifetime of the state. This is not really an uncertainty in that sense. Delta t is a lifetime of the state.
Okay, ma'am.
And you're not very convinced. This is a little bit twisted, I understand. But if you think about it, you'll see it's not that difficult. So delta E is the energy spread of the state. Okay. So that is more directly related to uncertainty in energy. But delta T is the lifetime. So it's not exactly an uncertainty in itself, but it is related to the uncertainty in measuring the properties of the system.
Sangita,
Yeah.
I'm here, so.
Okay.
No, it's okay. If you want to complete something, you complete it, right?
No, I completed.
I just wanted to inform.
I
Just wanted to inform. You complete it. I'll take a minute. You can. I'll take just.
No, we are fine. It was just they were asking questions, so I was answering. I am done with the teaching part. So I'll stop the recording and restart it because there will be different topics.
You ask Pankaj or something. I'll just.